All right, so let's look at the quiz. So it says, in which of the following sentences is work used in the scientific sense? Okay. So in the scientific sense, we always said that work can only be done if an object is displaced. So it says holding a heavy box. So if you're holding a box, the box is not moving in any direction. So because it's not moving, that choice is wrong. A scientist works on an experiment in the laboratory. Well, that's not even pushing something in a particular direction. Sam and Rachel pushed hard, but they could do no work. So even though the box didn't move, they didn't do work because there was no displacement, and that's what we talked about in physics. So this is the correct choice. Sam and Rachel pushed hard, but they could do no work. See, that's the scientific sense. In everyday language, if you said you pushed and something moved, you would say you did work, but that's not the scientific sense, right? And then the last one, John learned that shoveling snow is hard work. Did he actually shovel the snow? It just said he learned that, okay? Number 2, and you know what's funny is I put these types of questions on the test because I thought they were really easy. And for some reason, these questions ended up confusing some people. And I remember when we first talked about work, we talked about, the difference between, like, what work means in science and what it means in everyday language. A force does work on an object if a component of the force, well, let's draw a picture. Here's an object. So the displacement has to be in the direction. So even if I'm pulling at an angle with a force and the object moves this displacement, remember that component, the component of the force going in the direction of the displacement, that's the work. So now when we look at the choices, it says is perpendicular. Well, if the force is perpendicular like this and it's moving this way, that's not going to do any work because the force has to be in the direction in which the displacement is. So that choice is wrong. Is parallel to the displacement. Yeah, see how the x component is parallel to the displacement? When you're reading something, if you're not sure about it, if you draw yourself a little picture like this, you see how it helps to visualize by drawing a picture? What's parallel, what's perpendicular. Don't just read the words and figure it out because, this class is physics. And, a lot of times it's hard to visualize something in your head. So first of all, perpendicular, I know nothing's perpendicular, and then parallel to displacement, the object moves along the path that returns its object to the starting position. Well, if it goes this way and comes back, I have positive and negative work, and then the net work would be 0. Okay, so that choice was a little tricky. All right, number 3. Work is done when the displacement is not 0. Okay? If it's 0, there's no work. The force is 0, and the force and displacement are perpendicular. Again, you might want to draw a picture. If the sign of work is negative, and this was something we went over, I showed you the little pictures in the book, and we went over this, that if the sign of work is negative, the displacement is in the direction opposite of the force. I showed you this in your textbook. I said, this is where maybe having the little pictures might help you to conceptualize that. Okay? So I'm not really sure because that was something I made sure that we went over. Number 5 is like a typical physics problem in that this is what you see on standardized tests. I don't know if some people misread this word and, but what it said was ball A has triple the mass and speed of B. What is the ratio of the kinetic energies? So what you do first is you write the equation. So kinetic energy is 1/2 mv squared. And if you look there, that was the work that I did when I did the key. So you're tripling the mass and you're tripling the speed. So if they weren't tripling the speed, they wouldn't write it. They would just say the mass is tripled. They wouldn't say, I'm tripling the mass, comma. Why would they even mention speed? So some of you maybe didn't triple the speed, but the speed and the mass are both tripled. So now with the next ball, I have 1/2 3m times 3v squared because the mass and the velocity are both tripled. So 3 squared is 9, and 9 times 3 is 27. So when you're doing a problem like this, what stays the same? Well, the 1/2 is the same, The mass is the same, and this, so the difference is 3 squared times 3, because the 1/2 is the same, and that's how it came out to be 27. I told you, there's always going to be problems like this, where you have a basic equation, and, you know, they're saying, what happens if this is doubled, or this, or that? And we've had something like that on either a quiz or a test almost since the beginning of the year. So you don't try and do that in your head. This was the work that I did when I did the key. Did I do it in my head? Did I do this in my head? No. And I've been teaching this class for 26 years, and I still write it down. Because when you write it down, you're not going to make a mistake. In which of the following scenarios is work done? So if I'm holding something, am I moving it? And it was funny because I remember showing you the book, and we were talking about work. And remember, I lifted the book, but then I walked across the room holding the book. Remember that? Okay? So I thought, oh, everyone's definitely going to get these right, and those were the two that were most missed. And I thought, oh, these are easy because you don't have to do, like, problems and stuff like that. You just have to understand work, and these are the ones that most people miss. And I was like, what happened? So it says, which of the following scenarios is work done? A weightlifter holds a barbell. So the key word there is hold. He's not moving it. Is it moving up or down or left or right? No, so there's no work done. A construction worker carries a heavy beam while walking at a constant speed on a flat surface. Remember, I held the book and I walked across the classroom, and we said no work was done because I wasn't pushing or pulling the book horizontally because that was the direction it was moving?
I thought it was like so that it displaced.
No, I even showed you that in class. I took the book, I picked it up. Because the force, which is the force of weight, was acting in the same direction as the displacement vertical, we did work. When I carried the book across the room, I wasn't applying a force carrying it. I was just holding it. So there has to be a force going in the direction in which the object is displaced. When I'm carrying the book, I am not pushing or pulling the book. And that's why I showed you that in class. Okay, a car decelerates while traveling on a flat surface. Okay, so this is the correct answer because I'm moving in the direction which is causing the car. Remember, F is equal to ma. So deceleration, that means the acceleration is negative. An acceleration is caused by a force. The force is going in the same direction as so this one was tricky because when you read it, you have to say, okay, there's an acceleration, and you had to think about it a little bit. But even if you didn't, you would read a student holds. I'm holding a compressed spring. Is something being moved? No. So even if you weren't sure about this, just reading all the wrong choices, you could have gotten the correct answer. Okay? Number 7, in which of the following scenarios is no net work done? Okay? So the car accelerates down a hill, so that force times that displacement, that's going to cause work. A car travels at a constant speed. Now, at a constant speed, what does this mean? This means the acceleration is 0. Now, this goes back to, what, Chapter 2? Chapter 4? The rest of the year in physics, should you forget that when constant speed means the acceleration is 0, when something's going in a straight line? Should you forget that? But for some reason, when we have a test on something, we think, oh, we never need to know that information again. But that's not true. So whenever you see something's going in a straight line, like this, so a car travels at a constant speed on a flat road, that means the acceleration is 0. If the acceleration is 0, are we then having a force that's causing a displacement in a certain direction? No. So that's why this one is the correct choice. If a car decelerates, this one again, there's an acceleration causing that displacement, and then a car decelerates as it travels up a hill. Now, first of all, if you weren't even sure the answer, you see how these are all similar? See how A, C, and D all kind of do the same thing? Did you notice that? What's funny was in this, the wrong answers that people chose, because a lot of people missed that one, there was no particular wrong answer that people chose. Okay? Some people thought, ooh, the difference is it was on a hill and not on a flat road. Okay? This is physics. We're not going to see things up a hill, and that's going to make the difference. Okay. Number 8. So this one was just a calculation. A construction worker pushes a wheelbarrow 5 meters with a horizontal force of 50, and it says how much work is done. So I didn't even write this because I did this in my head. W is equal to FD, so it's equal to 50 times 5, which is 250. All right. So that's the multiple choice. Now let's flip over to the back. Now the FRQs, the numbers are just different. So Mr. Frank pulls a 60 Newton box of One Tribe T-shirts a distance of 239 meters along a level floor of the courtyard at a constant speed. A 21 Newton force is exerted on the box. So I'm not really sure what happened here. Some of you do like a free body diagram, you did friction, you did an inclined plane, and I was like, what is that? Okay? This was not meant to be a difficult problem. So the picture for this problem looked like this. Okay, so Mr. Frank is walking on the courtyard, and he's dragging a box of T-shirts, and this is the angle from the horizontal. So all this was, you know, F is equal to FD cosine theta, and that was it. That was all you had to do with this problem. When I looked at some people's work, and I'm seeing stuff like this, and I'm seeing like F, you know, FA, F of F, FN, you know, and all this other stuff, I was like, what is all that? You know, when I made these questions, did I make them up to try and trick you? No. Did I make them up to be hard? No. These were from the first homework assignment we did. W is equal to FD cosine theta. I don't know why some of you think, like on the FRQs, I'm trying to make impossible FRQs. I am not. Okay? I'm just trying to see if you understand, if you did the homework and you understood some of the basic stuff. Any question on this? All right, the next FRQ was, I thought, even easier. The next FRQ was just kinetic energy is 1/2 mv squared, and that was it. I saw people with free body diagrams, FA, FF, you know, FG, normal force, and I was like, why is there a free body diagram for this? This is energy. There was nothing about like friction or anything else. So this one was kinetic energy is 1/2 mv squared. Oh, I forgot something on the last FRQ. So where did a lot of people mess up on this FRQ? Some people who wrote the right equation, when it says Mr. Frank pulls a 60 Newton box, that is the force of weight. Now, if the box is moving across the courtyard like this, does the weight have anything to do with the problem? No. No. The box is not being displaced in that direction. So then it said that the force that's pulling, remember, a 21 Newton force is being exerted. So a push or a pull is my applied force. So this is the force that's acting in the direction in which the object moves, and it's the x component of that force. So that's why it's FD cosine theta. So if some people use the wrong force, okay, but you know, if you did the wrong force, you got everything else wrong. So I think you lost like half credit on that problem. And then the other one, I'm not really sure why anyone would miss this problem. I mean, not even knowing the equation, kinetic energy is 1/2 mv squared, because that's all that was about. And that's it.